Okay, she tells me I can begin. So how did you do? You can see my favorite one here, the marshmallows, was a type of foam. Some of these, you've heard these terms before. You've heard foam, you've heard aerosol. You might have heard emulsion before. So now you have what those things actually mean. A sol, solid and liquid. You can also have a sol that's a solid and a solid. And specifically, it's a solid sol. So dry paint as an example of that. Do you ever think about jelly as a solid and a liquid? Interesting thing, right? So moving on to colligative properties of solutions. So colligative properties of solutions are really unique properties. These are properties that depend on the solute or ion concentration, but not, underline, not on the identity of the solute. It doesn't matter if the solute is sodium, if the solute is glucose, if the solute is dimethyl ether. It doesn't matter what the solute is. It only matters how much of it is in solution. These properties of solution, these colligative properties, osmotic or osmosis is one of them, or osmotic pressure, freezing point depression, and boiling point elevation. I'm hoping you'll remember them as freezing point depression or boiling point elevation, or osmotic pressure increase. So those are some ways to try to remember them that way. So colligative properties, like I said, doesn't depend on what the identity is, but how much of it. So we have to take that into account. We have to think about what the component is, and does it break apart in solution. So the one thing here is glucose. Glucose, C6H12O6, is a ring structure. Actually, I had originally planned to draw it on the board here, but I can't because I'm focused in on with the screen. But maybe I'll try to draw it later for you, so what glucose is. But glucose as a solid, when you throw it in, doesn't break apart. As I think I did draw glucose for you before, it has lots of hydroxyl groups to it. So it forms hydrogen bonds in aqueous solutions, so it readily dissolves. So when you put the solid into water, it readily dissolves into an aqueous form. And since it doesn't break apart, we're going to give it a value, an I value of 1. There's no special name for it. We just say I is equal to 1. If I take sodium chloride and I throw sodium chloride into water, when sodium chloride dissolves in water, I get sodium ions and chloride ions. For every sodium chloride, I get 1 sodium, 1 chloride, or 2 total particles. So I equals 2 to indicate the number of particles that I get. What's important with colligative properties is how many solute particles. It doesn't matter the identity. In other words, sodium ions in solution behave the same way in terms of colligative properties as chloride. So you look at the two of these things as the same thing. They're just particles in solution. So I need to know how many of them. So 1 sodium chloride, 2 particles. Calcium chloride. When calcium chloride dissolves into water, I get 1 calcium ion and 2 chloride ions. Remember, that 2 tells me I have 2 chlorides attached to balance out the charge, the +2 charge on the calcium. So I equals 3. The significance of this is the nature of the solute doesn't matter, only the concentration of the solute. So if I know that I have 0.1 molar sodium chloride, I have 0.1 molar sodium ions, and I have 0.1 molar chloride ions, or my total concentration of particles is 0.2. So that's where we're going with this. So the first of these that we're going to look at is osmosis. Osmosis is when you have water movement across the semi-permeable membrane. And it's shown in this figure here. So all these little circles, blue circles, represent water molecules. These big purple ovals represent glucose molecules. So we have glucose on this side, we have water on both sides, and we have pores here. And if you notice, only the water molecules can pass through this semi-permeable membrane, through these pores. It's semi-permeable because the glucose can't pass through it. And so we have water is constantly in motion, and they're bumping off of one another, and they're bumping and bumping, and come to a hole, and it can pass through, and then it's on the other side, and it bumps and bumps. And so water molecules are moving in all directions. And so as these things moving back and forth, but it turns out, actually, that this water molecules aren't moving equally back and forth across this membrane. Because the glucose molecules are here, the water is generally moving more towards the glucose than away from it. So what's happening is there's a net flow of water towards the glucose. What it's trying to do is dilute out the glucose concentration. And a great experiment for this, I don't know if you saw this when you took your anatomy and physiology, is you take a thistle tube. This is a thistle tube funnel, or a thistle tube. And you can attach a semi-permeable membrane to this end of it. So you take the funnel, usually what you do is you hold it like this. You fill it up with molasses or a glucose solution. You put the semi-permeable membrane on it, and you stick it down into a beaker of water. And what happens is that, as shown here, you can see the water molecules are moving back and forth, but more water molecules are moving up than down. And as they do this, they're diluting out the glucose concentration, and so water is moving in, and you can actually, over time, measure how far it's gone, and you can get a rate at which this solution is rising inside that thistle tube. When equilibrium is reached, which means that the net flow of water up is the same as the net flow of water down, is when the pressure, the osmotic pressure, has been balanced. So you have to imagine that as water flows in here, this thing is moving up. There's air pressure pushing down on this. Furthermore, there's the gravity because this solution starts to weigh more and more. And so you hit a point where the two pressures are equal, the osmotic pressure as well as the force of gravity and the atmospheric pressure, and this thing stops moving. And so that's the osmotic pressure. How much pressure do you have to apply to stop the flow of water moving across that membrane? So osmotic pressure is a colligative property. One way to express it is through osmolarity. So osmolarity is a colligative property. Osmolarity is defined as the molarity of the solution, that's the capital M. Remember, molarity from last lesson is moles per liter times I, which is the number of solute particles that are there. So osmolarity, abbreviated osmol.